So welcome everyone to the first CHASC. It's not quite a talk, a discussion, colloquy, whatever you want to call it. It's being headed up by Josh. Sorry, not Josh. Andrew Saydjari.
Saydjari.
Okay. Who is a grad student about to graduate from Harvard. He's been working with Doug Friedbeiner. And I should let you know that Andrew is a reigning champion of the Astrostatistics Interest Group Best Student Paper of the Year contest. He will hold this thing at least until July or whenever the next JSM is. So welcome, Andrew. One other thing. So the way this works is, like I said, it's supposed to be a discussion more than just a seminar. So everyone, you're welcome to interrupt, ask questions at any time. We have technically it's supposed to last an hour, but it's okay if we go over a bit. We have an hour and a half time allocated, even though the actual budget is about 40 minutes, 45 minutes. But and with that, Andrew, take it away.
Okay, great. Can everyone hear me okay online on the owl? Yes?
I think so.
Yeah. Okay, no one has said anything. All right.
I saw a few councils.
Thanks for having me. Today I'll be talking about a recent project and paper that we put out on measuring the 8621 angstrom diffuse interstellar band in the Gaia radial velocity spectra. And I'm mostly going to be telling you about the methodology of how we obtained a clean catalog by marginalizing over different stellar types. So feel free to focus me on whatever you find most interesting, but that's what I'll spend most of my time on. I really like to let the data do the talking for itself. So I wanted to start the talk by putting the data first and telling you about the data that we'll be using. The Gaia satellite has obtained a lot of data. One of the data products it's obtained towards millions of stars are the radial velocity or RVS spectra, an example of which is shown here. And so you can see that this spectra is dominated by three main features, the so-called calcium-2 triplet, which is how Gaia actually measures the radial velocity of a star. Now, there's a lot more information in these spectra, though, than just measuring radial velocity, and we're actually going to be focusing on this region here, which I've blown up in the bottom panel. This spectra is what you would see if there was nothing between us and the star, but we know that there are small molecules associated with gas and dust that absorb light in the interstellar medium and have these features that we often call diffuse interstellar bands or DIBs. And the one that appears in the radial velocity spectrum has a contribution that I'm showing in red here to the spectrum. Now, one of the points I want to make, just flipping back and forth a little quickly, is that this is a very faint, very broad feature relative to the highly structured and much larger background. And so this is the general problem that I'm really interested in, is how do we tease out small signals on top of strongly correlated backgrounds? And that's what the method that we'll be talking about will be trying to do. Okay, a little bit more about the actual data that we have in hand from data release 3. This is the distribution of the sources of spectra that were released on the sky in terms of galactic longitude and galactic latitude. You'll see it's extraordinarily non-uniform, and that's because most of the sources released in DR3 were calibration sources that were cross-matched to things like TESS and Apogee and GLA. And so you can see a lot of those footprints imprinted onto the spatial distribution of sources that were released. This top-down view into the galactic plane is just showing you that most of the sources are within a kiloparsec or two, as you'd expect. As part of data release 3, they released a very wide range of signal-to-noise ratio distribution of the stellar spectra. And so this x-axis here is the stellar SNR of the spectra, and I've shown a dashed line here for everything to the right being stellar SNR greater than 70, and that will be extraordinarily important later on in the talk. But the most important part that you can see here is that the majority of the spectra that have been released are to the left of that line. They're low signal to noise. And if we want to take advantage of them, I'll argue that we really need methods like the one that I'm introducing. To hammer this point home a little bit more.
Sorry,
yes.
Can you turn off that light?
Oh, the front light. Yeah. Perfect. Okay, much better. So to make another point on the data release is actually quite limited for DR3. We receive only the continuum normalized spectra, and there's no way to undo that continuum normalization, and there's no release of the code that explains how the continuum normalization has been done. So as a function of stellar SNR on the x-axis again, on the y-axis, I'm showing you essentially the continuum level to which the spectrum is normalized. So ideally, that'd be like flat at 1, and they'd all have the same continuum normalization. But it turns out that in the processing pipeline, there are clearly two different modes. This is a log histogram. So, okay, this top mode is dominant above stellar SNR of 70. But as you begin to get into the low SNR mode, there becomes some switch in their pipeline, and then there's a second very important mode. And so this heterogeneity in the upstream processing, in terms of the way the continuum is handled, is really complicating for trying to model these spectra. And I'll show you that essentially what we do is we just try to close our eyes and marginalize over that uncertainty and still make detections despite it. Okay, so let me make this point about SNR 70 a little bit more clearly. This is a stellar spectrum that's high signal to noise. Looks great. You see 3 calcium triplets. And then you have this very big DIB feature that's about a 10 sigma detection. Okay, and this is the regime that most DIB catalogs have been working in for the last decade or so. The problem is that a lot of our spectra are by construction along dusty lines of sight, because that's where a lot of these diffuse interstellar bands are. They're coincident with dust.
Can I ask a quick
Yes.
question? So I noticed the red line is your model.
Yeah, the red line happens to be our model. Yes.
So does it, is it okay for it to be just a sort of a wide scale match rather than, does it have to match? Does it not?
Oh, this is the diffuse interstellar band model,
Right.
which is just a big, essentially a model here as a Gaussian.
Yeah.
We have a match to the stellar lines as well. I'm not showing you the stellar component.
Oh, okay.
Right, so this plus a stellar component equals the spectrum.
Understood.
Yes, no, that is not a model of any one stellar line. That would be a very bad model. These diffuse interstellar bands are importantly much broader than the stellar lines, and that's part of what makes them hard to measure. Okay, so I was ramping up to telling you that all of our lines of sight are by construction dusty, which means that there's a lot of extinction, which means that by definition, you're not getting a lot of light from these stars. And so you're almost always in the low SNR regime where you have the strongest DIB features, and yet we're not taking advantage of those spectra. So here's a spectrum that's only SNR of 40. It's clearly much noisier than the last one, but this diffuse interstellar band feature is actually larger amplitude. And so using our method, you get potentially an 8 sigma detection. I think that seems pretty reasonable here. There's a very strong evidence that there's a DIB in this spectrum, even though it's harder to actually see the stellar lines and the stellar SNR as lower. So we want to be able to use these spectra. And the reason that people haven't been able to do that for the last little while that people have been making these DIB catalogs is that they have to commit to a single best fit synthetic stellar model that they fit to the whole stellar spectrum. They divide that spectrum by the best fit, and then they fit a Gaussian to the residuals. That's the standard way that these catalogs are being made. And so that requires that you have high signal to noise in order to fit the best fit spectrum to the star to divide it out. But if you're just interested in saying, is there a DIB here or not, and how much equivalent width is in this DIB or the integral area under the curve, you don't really care what the stellar model is. You're happy to marginalize over the stellar models, and that's what we do.
I have a question. Sorry.
Yes.
It's probably a very trivial question, but your red line is the model, and the cyan is the data, right? So why you don't have the DIBs where we see very big deviations? There is like the DIB, which is red DIB, but then there are all the other deviations in the bottom line.
Those are the stellar lines. Those are iron lines, for example, in the star.
Okay, all right. So
we have a model of the stellar features that I'll show you later, but this is only the component coming from the diffuse interstellar band.
Okay, so all the other lines are identified and you know about them, and we just looking for this DIB.
Okay. That's right. We have a bit of a data-driven model for the stellar model, but yes, they are also identified in line lists.
Okay, yeah, I don't work with the optical spectra, and it's kind of tricky.
Also, interstellar spectrum.
Yeah, interstellar and optical spectra.
Interstellar.
Some might call this near infrared. So,
yeah, optical spectra. I just do X-rays, so. But yeah, okay. So this is I understand now. So these are all the lines which that they are there, and then the deviations which you call DIB is this extra feature you're looking for.
That's right. Yeah.
Okay.
Yes.
So your model kind of has multiple components, and you're just showing this one line is just DIB, and the other components are just.
I'm not showing you the other components. I will shortly. But
Okay. Are you done? So I have a question. So
yes,
in the upper panel, like around the big thing around 8500 or 8550.
Yeah,
there's two of them, right? So how do you distinguish between let's say a flat continuum and something which might be causing an excess absorption.
Wait, how do we model the calcium lines?
No, that's, yeah, I mean, calcium, yes. What I mean is some of this. I mean, what if you have something?
Do you want my pointer?
No, I know. Hang on, let's see. Yes, suppose this were actually like this. How can you tell if there is no bias in the continuum that might be caused by something else?
Right. Okay. So maybe I'll rephrase your question and say, what if the DIB happens to exactly coincide with the stellar feature? How would you know? As I'll explain in a second, we build a covariance matrix to describe the stellar component, and we ask how these different lines covary with each other. So, if you have a high metallicity star, the iron lines are deeper, depending on the temperature, and so if the deviation were significant relative to the expected covariance of that line, that one calcium line with the depths of all the other ones, you could detect it by saying, oh, it's much deeper than it should be. Maybe there's something under it that's adding to it. But if if this line were totally isolated, uncorrelated with anything else, and there happened to be a DIB appearing behind it, I mean, you would have a very hard time detecting it. Your signal to noise for the detection would be quite low. So that's just part of the failure modes. But in this case, these diffuse interstellar bands are generally correlated with each other, so you could latch on to another one. And generally, a lot of these lines are from a species that you see other lines in the spectrum and can correlate them. All right. Okay. Cool. So let me just say that the DIB model, the DIB catalog that the Gaia team put out for the radial velocity spectra uses conventional method. They took a best fit stellar model, divided the data, and fit a Gaussian to the residuals. And let me show you that also has a problem beyond not going to low signal to noise by showing you two different parameters in that catalog. So one is the center wavelength of the Gaussian that was fit to the residuals in the stellar rest frame. That's on the y-axis. And then the second is the width of the Gaussian that's being fit. That's on the x-axis. And this is a 2D histogram with log normalization. So what you can see here is that even within the highest quality sample that they released, which is this gray box, there's a strong trend in the data towards a pileup at the top left-hand corner. This trend in the center wavelength corresponds to velocity offsets on the order of 50 to 100 kilometers per second. So this is pretty significant. And this pileup in the top left-hand corner and even in the bottom left here, as you move over the high quality boundary, becomes even more obvious, and there become multiple pileups at specific wavelengths in the stellar rest frame.
So what do you mean by pileup?
I just mean this is large density, the yellow points.
Oh, okay.
The yellow density points. Okay, this is, yes.
Why is it high quality?
They have released a subset of their catalog that they call high quality.
And this happens to be a box.
Yes, they make cuts in parameter space that cause it to be a box. There are also some other upstream cuts. So inside the box, I'm applying those upstream cuts, and outside the box, I'm not applying those upstream cuts. I will show you in a table the exact cuts, but essentially this is the catalog they tell everyone to use. And then this is the rest of the catalog on the outside. And I think it's clear, and the reason I show both of those is not just the high quality, is that you can see that it's a cutoff attempting to remove these features that are just outside the box, but it doesn't do a good job. There are still features that are clearly in the stellar rest frame that are leaking into the high quality catalog, and it's being pulled towards that feature. Yes.
Oh, so that high quality box is just like chosen like by them
Yes.
without like kind of like justification.
Well, the justification is that we expect these diffuse interstellar bands to have a width of around 1.9
Oh,
angstroms.
got it. I see.
So they took some region that they thought was physically reasonable, and they believe the center wavelength is sort of centered here. So they took a width in this direction that's somewhat reasonable and said we should exclude everything else. But I would argue that this shows a clear impact of stellar lines on conventional methods of DIB modeling. The fact that you're getting pileups at exactly certain wavelengths in the stellar rest frame is very suspicious. And let me confirm those suspicions by showing you some line lists. The set of green lines are lines in the Gaia model, and the set of magenta lines are a subset of the lines that are not in the Gaia model. And you see that these two biggest pileups on the right-hand side correspond to known iron 1 lines that aren't in the Gaia line list. Okay, so I think this makes it clear that if you're just trying to fit a Gaussian to residuals, you're very sensitive to accidentally fitting stellar features that you weren't modeling very well, and then having these unfortunate false detections of diffuse interstellar bands. In contrast, we introduced a method that we call magics that I'll describe on the left here, and our catalog clearly has no such pileups at any specific wavelengths in the stellar rest frame. And further, it actually has a distribution in the lambda DIB direction, which is exactly what you'd expect based on the dispersion of the interstellar medium, which is around 49 kilometers per second. Okay, so I'm going to pause here because if the paper and the talk were one slide and one figure, it would be this figure. And the talk will all be entirely about how to move from this regime on the right, which I think is not a very good catalog, to the catalog that we produced on the left, and about that methodology. So any questions here?
Going by this
Yes.
picture, is your catalog much smaller?
It's not actually. In terms of the high quality sample, the counts are actually quite similar. So we have about 7,700 and their catalog here is about 9,700 on the exact same data. So it's 2,000 smaller, but it's the same order of magnitude to me. If you counted detections out here that they argue aren't good detections, then yes, it's much smaller, but they argue you shouldn't consider them. So.
Yeah, okay.
So is there any reason a priori to believe that those structures on the right, they're false?
Well, the fact that they line up exactly with known iron 1 lines that aren't in the stellar line list that Gaia uses, I think is pretty strong evidence that they're not. And these diffuse interstellar bands should be in the dust frame, rotating with the gas, co-rotating with the galaxy. They have no reason to be in the stellar rest frame unless they happen to be emitted at the star with 0 velocity, which I think is highly unlikely.
So I have two quick questions. First, just curious, what would be a low quality one? When they say that's high quality, what would be low quality?
Oh, you can't. So here's a low quality one, like right across the gray line where my cursor is now. That would be part of their low quality catalog.
I cannot see it online. Is that?
Oh, you can't see my cursor?
I guess if you go.
Oh,
to
you mean where your cursor moves
Yeah,
to?
where my cursor is. That would be what they would call a low quality detection.
But why? What's low but quality about it?
Well, it has a very, very narrow width, which is closer to a stellar line width than a diffuse interstellar bandwidth. So they view it as not very competent. There's no statistically motivated argument for it, if that's what you're asking for.
So
Well, it's just what it needs.
Sorry, what?
Well, the reason I'm asking is the first is curious. Second is I assume your method is going to improve upon. But so what's the metric here? So if there is something called a low or high, I assume there's some metric for which you're going to show you will produce even higher quality. Is that the game here? Or I'm misunderstanding.
Okay, the game is not having stellar features that are misidentified and calling them dibs. So that's the main name of the game. We actually have a statistically motivated notion of the SNR of our dib detection, which is not provided by the Gaia dib catalog. They instead make these very qualitative box cuts to try to distinguish between high and low. And that doesn't have a well-defined metric, whereas we do have a well-defined metric. So one of the main changes is that we actually have a metric for the quality of a detection, and they don't.
Okay, so but then using your new metric, if you apply to their old methods, you will show you can show that theirs is pretty bad.
Yes, that will be one of the main conclusions at the end in terms of the astrophysics, is that they claim that there are multiple 10 sigma detections in places that there absolutely are not, and we have physical prior to believe there should not be 10 sigma detections.
And they're not distributing. I'm asking this not with any real knowledge, but just in terms of general principle here. So they're not disputing your metric, because sometimes you show something's better using your metric. They say, hey, that's your metric. That's not our metric. Is there some consensus here?
We've spoken to the people who produced the original DIB catalog, and they seem to clearly agree that we have improved upon the catalog by removing the stellar lines, and that our metric is good. So there's not really any contention in terms of the public data. One thing I should make clear is that only 1 million of the 5.5 million RVS spectra have been released. So there's still some contention between the two groups about what's going on in the private data that we don't have access to. So I've restricted my entire discussion here to all the public data that we can compare apples to apples processing of the two different pipelines. Although a subtle fact is that the data that they released publicly isn't exactly the same continuum normalization of the data that they used. So we can't make it a perfect apples to apples comparison. That's as close as we can do.
Thank you.
Yeah.
One other question.
Yes, please.
So I noticed that on average, the width of the DIBs has decreased in your recalculation.
The center here?
Yeah.
Yes, it has.
Everything seems to have moved.
Shifted a little bit. Well, if you take a probability weighted density, because of the high density up here, it might actually be closer to the center. But you mean of these detections?
Yeah.
That it's centered over here versus here. Yeah.
Oh, okay. Yeah. Okay. Yes. So it's all right.
The problem is that these probably aren't real detections. They're stellar lines. And then these are clearly being impacted by those stellar line detections. So it's really hard to know
Got it.
whether or not you should trust their width. And in fact, I'll argue that I think basically no other div catalog has given really rigorous or really interpretable measures of the width of the Gaussian, the width of the div. And I'll argue that I think that we have started down that road with this catalog and begun to be interpretable. Although it's very hard to measure a second order moment of a faint, broad, low amplitude thing. But I'll show that it's at least what we provide is interpretable. Okay. This is an important slide, so I'm happy to take any other questions. Okay, well, I will jump right into the methodology and explain to you how we did this. So the name that I put above the catalog is the name of the method, and we call it Marginalized Analytic Data Space Gaussian Inference for Component Separation, or for short, MAGIX. And this lives in the set of family of techniques that often go to the name of generalized Wiener filtering and the like. But let me just explain to you what the method is doing. It's quite simple. You suppose that your spectrum is a linear combination of components x sub k, and those x sub k are drawn from a high dimensional Gaussian characterized by a covariance matrix c sub k. Now that high dimensional space that we're working in is the actual data space, the set of 2000 wavelength bins that your spectrum is actually living in. And your only prior is that the x sub k are drawn from that space, and that the sum of those x sub k exactly equal the data. So you can exactly get back the data that you took. It's really hard to show these high dimensional Gaussians. What I can instead show you is the covariance matrix that describes the distribution. So let me show you that for the stellar component. The way that we obtain the stellar model, the stellar prior, is by taking high signal to noise, low reddening stars from the actual set of spectra that were released, and just computing XX transpose, right? That's how you get a covariance matrix. This is a 2K by 2K matrix. And you'll see that it's dominated both on the diagonal and the off-diagonal correlations by the calcium-2 triplet, which was the big feature I showed you at the beginning. That's not what we're interested in. That's a stellar feature. We're interested in diffusing their stellar bands. I'll comment that these matrices might scare you being so big, although 2K isn't all that big, but they're actually generally low rank. They're quite low rank. Their eigenspectrum is quite steep, so that they admit a very nice approximation, and that actually adds a lot of computational speed up. So in fact, we should look at the eigenvectors, one of the eigenvectors. I'm pulling out the third one here. And the bottom panel, I'm zooming in around the div feature, just so you can see all the little bumps and wiggles. Okay, these bumps and wiggles are stellar lines. And you'll see that some of those bumps and wiggles are falling on the green lines, the lines in the Gaia line list. And some of them are clearly not explained until you add these magenta lines that I was arguing aren't in their line list and are exactly coincident with these pileups. And you see that those are coincident with stellar features in our data-driven stellar model. In terms of the bumps that you see here in our spectrum. Sometimes, yes?
Just a quick question, if I understand this. You're saying data-driven model, you're saying you assume the covariance of your prior is exactly the same as you observed?
We observe low reddening, high signal to noise stars, and a large range of types. And our covariance is built based on all of those different spectra and how pixel I and pixel J in that spectra correlate with each other across the training data, which is observed, which is a subset of the observed data. But it's high signal to noise, low reddening spectra. So there should be no contribution from the div, and it should only capture the stellar variability.
So another way of thinking about is that your replications in terms, I assume in the end you have some kind of uncertainty assessment will be assuming all the future data will be having shared the same kind of rotation, same shape. Is that right? Because you're fixing the covariance matrix.
That's right, but it turns out this covariance matrix is extraordinarily floppy and captures a large range of stellar types quite well. And I'll show that validation in the second section.
Okay.
But yes.
Are you limiting your stellar sample to a particular temperature range? Or something?
I'm not.
So why would it work?
Why would it work is a great question, but I'll show you that it does. Essentially, what's happening here is you're marginalizing over fluctuations in different lines in their amplitude. That's very well described by a covariance matrix. And in this high dimensional space, stars live in a fairly low dimensional space, right? All possible stellar spectra are not actually in a 2000 dimensional space.
Right, but if you change the temperature, you're likely to change the corresponding intensities.
Right, but that's very well captured by saying that dimension isn't very highly penalized in the covariance matrix. That those lines can change, and they change together in a very in a covariant fashion. So that's fine. And so I'll show you I'm glad you asked, but I will show you that I think one of the most important validations is that we show a very good stellar model as a function of a large range of stellar temperatures. There are certain temperatures that we can't model, like really crazy low and really crazy high temperatures, might not fit in a single covariance matrix model. And then you might make this covariance matrix depend on temperature a little bit and build a slightly different model around different temperatures.
Also, if you look at some very low mass stars, then you have what do you call them, molecular bands all over.
Yes. So we actually, some of these lines are cyano radicals, but yeah, when you start getting really cold, you'll have a lot of problems and really low mass stars. Exactly. So this is for all the stars that have RVS vector to them, which are mostly, FGK stars. So this is not like the hardest regime of modeling stellar types. We're trying to grab the most of them that we have lots of bright spectra to. Okay. I want to say one more thing is that people often will debate line lists and line identifications. And so you might say, how are you so sure that these features that are in your data-driven stellar model are actually stellar in origin, not just dust that got into your model? Here's a high resolution solar spectrum. And the two bumps that all the pilots were on are clearly very prominent features in the solar spectrum. So whatever you want to argue these features are, whatever label you give them, I'll argue that it's really clear that they're present from the star, that they're of stellar origin. And so this isn't to critique any one line list. All line lists are by definition incomplete. The point is that our approach avoids that problem entirely by not committing to a single line list and by not even committing to a single best fit stellar spectrum, but by instead choosing to marginalize over all possible stellar spectra described with this covariance matrix. And I think that's where a lot of the power comes from. And that gives us not only a mean estimate of each component, but also a full posterior on each component in terms of the covariance matrix, pixel I and j within the spectrum, and pixel I in one component with pixel j in another component, which is just shown by the formulas at the bottom left here. I want to say one more thing about the choice to model things this way, which is that this covariance matrix is actually a very flexible way of modeling. You don't have to commit to saying that your diffuse interstellar band that you're trying to model is a Gaussian. In this case, we've restrained ourselves to that to make the comparison to the catalog that Gaia released a little bit clearer because they did Gaussian fitting. But if you had a multimodal feature, a diffuse interstellar band, you could easily put that into the covariance. Pixel I and pixel j having that exact shape. It could be asymmetric. It could be a void profile. You're not restricted to anything here. It's a very flexible model, and that's something that I really like about this.
Well, let me just make a point before we move on. I agree with you that I think covariance is a great way to model this, but it seems like you might have already considered this. Maybe this turned out to be not important. You don't really have to fix the covariance exactly is where you observe. You can put another pri. You could put a hyperpri on this covariance centered at where you observe. That's in Prickle base, right? You can do the inverse Wishart. You can do all these other standards, and you end up with. I don't think the computation is going to be too complicated because you end up with like a T multivariate T kind of a distribution instead of Gaussian. I don't know if that's worthwhile doing it. Sometimes these extra steps does not really bring anything, but just methodologically having gone through the process, if you have that, will give you more confidence. The simplified version might just works as well. Just a quick comment.
I agree. We haven't tried that. We've thought a little bit about it, but it's a good suggestion. Okay, yeah.
So by modality, you mean that you could have multiple Gaussian added together, right?
Yeah, I meant like, there are two peaks, there are two different lines that are close together that create the diffuse interstellar band. So there's sort of two Gaussians of slightly different amplitudes next to each other.
Yes, okay, right.
Yeah, there are a few diffuse interstellar bands that look like that.
And another question regarding temperature. I can't really imagine how the covariance would change. Can you give me a brief intuition for that?
Yeah, certain lines will get deeper relative to other lines as you change the temperature of a star. And so the covariance matrix is trying to capture all those.
So mostly the brightness of those blobs will change.
Yes, that is the thing that this covariance matrix will marginalize over the best. Yeah. And changes like the name mentioned that adding in lots of new molecular features that weren't in our training set will not be very well modeled by this. And so by definition, these sorts of low mass cool stars are not going to be measured very well.
Yeah, if you were to throw in a whole bunch of very low mass envelopes or something, then the correlation between the calcium lines that you see here would sort of drop.
Exactly.
So you lose your efficiency of detection. So but then you mostly have, as you said, late G to early M. Maybe?
Yeah.
So it's,
but I would argue that what we should do is we should build a different covariance matrix model and then marginalize over those different covariances for training on stars like that.
Okay.
Yes.
Oh, this is like naive question about the covariance, component posterior. So
Yes.
that equation is just the exact form of the posterior of data, after we consider the data,
Yes.
not the any
That's right. So the data, you see
Yeah.
the data here is X-tote.
Oh, I see. So
And-
we do
and-
the covariance.
Yeah, so this gives you a mean estimate based on the data. This is the data,
Oh,
X-tote.
oh.
And then C-tote actually accounts for the measurement uncertainty. And so that's showing you what your actual uncertainty between pixel I and pixel J is given the measurement uncertainty.
Thanks.
So I think the idea is if you write down the model like so that the total flux that you're measuring, X top, right? Is the sum of various Gaussians, and you can analytically derive the posterior.
Exactly.
That's
You just
very
take a first and second partial of a log likelihood, right? Each of these things being drawn from a Gaussian gives you a likelihood. You can just differentiate it.
Thanks so much.
And that gives you both the mean and the covariance. Okay, I'm going to move on if there are no other questions. We spent
Actually,
Yeah.
actually, I do have a quick one that, am I correct that instead of thinking about you have a fixed covariance matrix at the data, I know we think about it, you simply have a constant pri on X, because that if you do it, you will be end up with using this a data covariance anyway. So is that, am I right that you could view it instead of a normal pri with observed data matrix as covariance, you think of that as a uniform constant pri, and if you just do likelihood to the inference, you will end up with the data covariance matrix as your covariance matrix anyway.
I'm not sure what you mean by a constant prior. I mean, the prior here is given by the covariance matrix C sub k, and it's certainly not flat. It includes it's some high dimensional ellipsoid in that space, but it is a fixed covariance matrix regardless of the data that you're then applying, and then the data modifies it, and you get these posteriors CKK and CKM.
Oh, so okay, so the CK so CK here is not directly computed from the covariance of X itself.
That it's computed from a training set, but it's not computed from the single data that you're actually applying it to. No.
Got it. Okay. I was referring to that.
CKK and CKM are computed from X in your nomenclature.
CK and the CM, they are computed from the same X.
CKK and CKM are computed from X, but CK itself is just your original prior regardless of X.
Got it. Okay. So I see. So when you say that, all right. So what I was referring to is that if you just put a constant pri, just like non-informative pri on X itself, you will end up with like computing the CK from the data itself. But that's not what you're doing. Your CK is from some other training sample.
Yes.
Yeah. Okay. Got it.
Okay. Good. Right. So rather than derive those equations, which I think we all know how to do, I just wanted to give a little bit of intuition for where they're coming from in terms of a problem that I think is a low-dimensional problem, because I like to look at low-dimensional problems. So suppose your data is a linear combination of two components, A and B, that are drawn from these Gaussians. You want to find the best A and B that sum to the data D given your data and your priors. Okay, and so I just want to show you that in 2 dimensions this is sort of obvious, especially when these covariance matrices are orthogonal. So if your prior is that the component A is basically along the x-axis, the component B is along the y-axis, it's pretty clear what to do here in terms of the decomposition. It's just a projection. You get your x component and your y component summing to your data. And the point is that you move from the simple notion of a projection to a posterior just because there's some width of the prior along each axis. This problem is slightly harder when these covariance matrices are not orthogonal. So here I've tilted A a little bit, but that's just a little bit of geometry. And that little bit of geometry is exactly what the formulas on the last slide are doing. You can map that one-to-one. Okay, so that's exactly what's going on here, and just in a high dimensional covariance matrix space. Okay, I want to say one more thing about the method, which is that there are certain, well, first of all, we translated the problem of component separation into a problem of specifying the C sub I, right, into these components C sub I. But there are certain variations in your model that may or may not be well described by a covariance matrix between pixel I and pixel J. For example, shifts in the center wavelength of the div are not very well described, especially if you're shifting over a large range, by just the covariance matrix of pixel I and pixel J. Similarly, breathing modes of changing the width of the div are not very well described by that. So there are a few parameters that we still sample over, that we parameterize these C sub I as a function of theta. And specifically for the diffuse interstellar band is the two that I just mentioned. So we still do some sort of sampling of the center wavelength because a priori we don't know the dust velocity. We essentially know the stellar velocity, but we don't necessarily know the velocity of the dust. And so we just scan that parameter and ask what the delta chi-squared is. And you have some normal, minimum, and you just take the width around that minimum as usual to give yourself the uncertainty. And we do the same thing for the width of the dip. So we scan, build a different covariance matrix for each sigma, scan, and find the minimum of the delta chi-squared. And so we actually scan this 2D parameter space as a bunch of 1D line scans. But we actually can compute the uncertainty from a full local 2D Hessian.
Just so I understand, so you're looking at a very small region of the spectrum at a time?
No, the whole spectrum. The whole spectrum is always being modeled.
But how are you fixing the sigma?
The sigma is of the dib itself, which is just some local Gaussian. So if you want to say that that's looking at something local.
Oh, okay. So
So
you
the
have
stellar
one
spectrum is
spectrum and one dip.
And one dib. Yeah. So we're only scanning 2 parameters of one dib.
Got it.
So this is one component that's changing. Yes.
Sorry, very technical question, but why compute the Hessian by finite differences?
Just because we have this chi-squared surface, so we just compute the Hessian via the chi-squared surface. Is there some reason that you do it another way?
Can't you derive it analytically?
Not when you're sampling over the parameters this way. This is just sampling over the grid. So the uncertainty per component we have analytically, but when you're having to just sample over these different the different C sub I as a function of theta, no, you just compute it numerically.
I mean, numerically doesn't mean that you can't do it like analytically, like with automatic differentiation or something like that.
You could do it with auto dip, we're not doing it with auto dip.
Okay. Yeah. Anyways.
Yeah, I don't think there's a real problem here. I mean, the uncertainties are quite good, and you'll see that we validate the uncertainties. Yeah, we can consider taking a look. Okay, so I've talked a lot about these components and sort of high-fluent language, and I just want to get back to actual data and show you what this looks like and what these different models look like. So the top panel is the actual data. Okay, I've just zoomed in around the dib. My first model is just to say it looks like a star plus a residual component. So this residual component is something that's consistent with the diagonal covariance based on measurement noise, and the stellar component is based on that stellar prior that I showed you earlier. Okay, and mostly what we've done here is we've obtained a denoise stellar spectrum, right? That shouldn't surprise you. And then this noise mostly looks consistent with measurement noise, except that you'll see that there's this dip here in the middle. Okay, this dip is exactly the contribution of the diffuse interstellar band. It appropriately looks quite small. But what's really exciting about this is that this dip is appearing in the residuals. And this tells you that unmodeled components that aren't necessarily star, which is our only component that we've explicitly modeled, are going to appear in the residuals because they're not consistent with this prior. And it actually shows up as having a large total chi-square per degree of freedom. So you can know and look for these features. And because these two components exactly equal the data, there's no loss. So this really preserves the ability for data-driven discovery in your spectrum. You're not throwing any of the counts away. You're not throwing any of the features away. You're just partitioning them into things you understand. And then all the things you don't understand or noise will come out in this last component. We can revisit the same spectrum under a slightly different model, which is that the data is equal to a stellar component, a diffuse interstellar band component, and then the residuals. And the main change is that now the residuals are flat, right? So this feature has now moved into its dib component. And I want to draw your attention to the fact that the stellar model hasn't changed significantly at all. And that's telling you that this feature was so inconsistent with the stellar prior that it basically pulled the stellar component at 0%. A small technical detail is that diffuse interstellar bands are actually multiplicative because they're absorption of the stellar light, which doesn't fit beautifully into a linear combination model. So instead, you use this red stellar component that you derive times your prior for what the dib absorption looks like to describe your prior on this dib times star component. And you can iterate with your new estimate of what the star looks like, and it converges in basically 2 steps. So it's not a big iteration because, in part because the dib is entirely in the residual, but it's an important detail. So what we do to then move to a catalog of diffuse interstellar bands is we just compare these 2 models. So we evaluate all 1 million public RVS spectra under both of these sets of models, and we ask what the delta chi-squared is. And then we take all dib detections with an SNR greater than 3.8 sigma, and I'll show you how we calibrate that number in a second. And we call those detections of a dib, and we make a catalog of their parameters. Now, it's important not to just look at the delta chi-squared, as I think most of us know, because you really need to first look at the total chi-squared per degree of freedom, because there are some spectra that are just not being very well modeled. And adding another component, adding some Gaussian to soak up some portion of that spectrum that you're not modeling very well, will lead to a large delta chi-squared But that doesn't mean that you actually know what you're fitting, and doesn't mean that you've actually modeled your spectra very well at all. So on the top plot here, I'm showing you the total chi-square degree of freedom, and you see there's a lot of stuff that has a pretty high value that isn't close to 1. And so our acceptance region is shown as these white dashed lines. These plots are versus the equivalent width, the center wavelength, the width of the Gaussian itself, and then the stellar SNR. So these are just different views of the data. And importantly, you see there are certain pileups here, certain overdensities at specific wavelengths in the stellar rest frame. So you can imagine that this is the Gaussian fitting some stellar line that wasn't being very well modeled. And even after adding the Gaussian to the DIB and having it accidentally identify the stellar line, it's still not very well modeled because the total chi-square degree of freedom isn't very good. So by actually keeping track of your chi-squares, oh sorry, I'll just say that this is the delta chi-squared for adding a DIB component. And if you weren't to do this cut that I'm showing you in the top, this is what you'd see. Again, seeing these pileups at certain wavelengths in the stellar rest frame. But after doing the cut, this plus or minus white dashed line here, what you see is the delta chi-squared looks very clean. And so our detection threshold is the red dashed line, and you see that it's very smooth in the lambda, the lambda direction, the center wavelength direction. There are no pileups. It's centered on the wavelength that we'd expect. And it's very smooth in sigma and stellar SNR. And then in the equivalent width plot, I'll draw your attention to the fact that all the detections are on the positive side. They have positive equivalent width, and that just means that you're seeing the feature in absorption based on this sign convention. And based on the energetics of this transition, you would expect to only see it in absorption and see no emission. Any emission would probably be a spurious detection. So we take this as a very, very great validation of both the total chi-square degree of freedom that we're reporting and the delta chi-square value that we're reporting.
So just so I understand, so between the first row and the second row, you're not making any.
The first row and second row are two totally different quantities. One is the total chi-square degree of freedom, and one is the delta chi-square.
And
there's no cuts being applied. So I'm just showing you, if you were to close your eyes and not think about how well you fit your spectrum overall, this is what your detection catalog would look like. It would have all these features in it. And the bottom row shows you what you do if you actually think about excluding chi-square.
And the last row is when you put your thresholds in the reduced chi-square space.
Yes, in the white dashed lines, exactly. Okay. So without further ado, I'll show you our catalog. I showed you only one view of it before, but I'll show you a slightly different view of the catalog. This is the equivalent width, the integral area under the curve on the y-axis versus, again, wavelength, sigma, and actually the DIB SNR, the delta chi-squared converted into an SNR. And you can see is that almost all the detections are positive. They have a nice distribution in sigma. And what I really want to show you here is that the DIB SNR, this notion of delta chi-squared, really is a good quality and a continuous quality cut on the catalog. Because as I said, these negative detections are likely spurious, and all of them are sitting right here at the detection threshold at like 4 sigma, right? If you just go slightly to the right, these 5 and 6 sigma detections are all positive and all agree with our physical intuition. So I think this is showing you that we actually have a pretty well-motivated quality cut. And if you're interested in, you can cut it at whatever point you want.
Sorry, what does negative equivalent width mean?
It would mean that you're seeing it in emission, for example. And based on the energetics here, you wouldn't see this in emission unless you're in a very, very hot region. Most of these stars are not passing through extraordinarily hot interstellar medium. So I would view those as spurious detections. Yes.
So kind of you should actually, so does this mean that you should enforce in your model positivity or something?
One could. We did not enforce positivity, we just let it go.
Okay, but that would be an indicator that this is needed for those types of.
Well,
or to exclude those models, which you can do via quality cut anyways. Okay.
Yeah, you can do it via quality cut. I don't think it's necessary. I think it's useful to see, what the scatter is in the negative direction. But there, you wouldn't. Personally, I wouldn't want to rule out possibly seeing it in emission. There are some hot regions that you might possibly see dust and emission from, and so because it's not totally unphysical, I wouldn't want to remove it. In this case, I'm telling you that based on the subset of stars that we're looking at, the subset of line of sights, you probably shouldn't be seeing it, which is why I'm pretty confident those are all spurious.
Okay.
And I've looked at them all mostly by hand, and I can tell you they're mostly spurious. Most of these are actually coming about, by the way, I'll just comment, most of these are coming about because of the really weird continuum normalization that's happening upstream of us, because they fit some crazy polynomial that doesn't actually leave a flat continuum. And I showed you a little bit of this, the variation in the continuum at the beginning. That's really what's causing every once in a while. Some of those features happen to be essentially as wide as the DIB. And then there's a little bit of enough of a benefit. It's a 4 segment detection, but there's enough. And you could argue that maybe I should be recalibrating this SNR to account for the fact that shouldn't be detected. But the number of false positives that we detect in certain regions, as I'll show in a few slides, are exactly the rate that we'd expect to see based on the cumulative distribution past 3.8 sigma. So I think it's actually a pretty well calibrated measure of signal to noise ratio. Okay. So this is the catalog overview that Gordian was asking about earlier. This is the high quality catalog in the second column, and our catalog, the Magic's catalog, in the left-hand column. And this is a comparison of the different cuts that were made by the different catalogs. And this is also sort of just a philosophical difference between the catalogs. So you of course have to apply some SNR cut. And in the high quality sample, they restricted to only stellar SNR spectra greater than 70. We use everything that's been released, which is down to SNR 15. And we apply a 3.8 sigma cut on DIB detections. They don't really have a DIB SNR, but if you compute the EW over sigma EW cut they do and try to convert that to a DIB SNR, they make a cut of about 2.86 sigma. And as I said before, you need to make some notion of cut on your overall goodness of fit. And we have a very nice, total chi-squared per degree of freedom that we make cuts in order to do that. Whereas they make these cuts on upstream flags from the GSP spec pipeline and on amplitude, lambda, and sigma, which is that gray box essentially that I showed you earlier. And that's how they try to cut out spurious detections. And so in total, we find 7.7 thousand, and they find 9.7 thousand detections in the public sample. But those numbers aren't exactly comparable because we search all of those very many low signal to noise stars, and they're restricted to only looking at the signal to noise greater than 70 stars. So they're actually finding a lot of detections that we would view as spurious in those high signal to noise stars. And a lot of our detections aren't accessible to them. And I'll show that in this plot on the right. So the DIB SNR is on the x-axis, the stellar SNR is on the y-axis. And again, this SNR 70 cut is shown as a white dashed line. And so all the detections that you're seeing down here in the bottom part of the plot, those are detections that we can access that conventional methods haven't been able to access before. These are very, very strong DIB features that just happen to appear in somewhat lower stellar to noise spectra, whereas the ones up here are ones that were accessible before.
So there's a huge difference in the samples actually.
There's actually a
half of the samples are disjoint.
That's right. It's actually a little bit more than that. Like we think that we agree on about 2,500 DIB detections.
Wow. Okay.
Yeah, and the ones that we agree on, both catalogs have problems and have spurious detections in them. The ones that we agree on are really definitive detections. Like if you're strict to that catalog, it looks great. But I'll argue that I think that our 7.7 thousand is a cleaner catalog based on many of the metrics that I've shown you. Okay. Yes.
How did you come up with the signal to noise ratio of 3.8?
Yeah,
I mean, 2.86 sounds very random, but 3.8 sounds also a bit random.
I'll explain how I got it.
Okay.
That will come. That will come shortly. Yeah, we are approaching 12, but it will come shortly. Okay. I just want to say one thing is that this isn't like entirely magical, despite us calling the technique magics. If you just show what the plots would look like if you made the no goodness of fit cuts. If you didn't make that total chi-squared degree of freedom cut. I want to show you that those pileups that we were seeing in lambda space, they look similar in the fact that you see pileups at certain wavelengths in the stellar rest frame if you were to not apply that cut. So part of what we're doing is that we're accessing lower signal to noise spectra, we're marginalizing over stellar types, and we're less sensitive to poorly modeled stellar lines. But if a line is so poorly modeled that we can't fix it, it would have appeared as a detection here if we hadn't made that total chi-squared freedom cut, which I think is the statistically right thing to do, which is why we did it. But I just wanted to show you that we have pileups and some of the same features that they do, and some of them that they don't. So like some of them agree, some of them don't, but there are clearly some stellar imprints if you weren't to do such a cut. Okay. I'm now going to move on to the validation section of the catalog, answering some of Gordian's many pointed questions. Any other questions on the catalog before I do that? No. Okay, great. So as part of validation, I find it always necessary to do synthetic injection tests. So to at least know that my model can recover something that I intentionally put in there and know something about. And that's what this massive panel figure on the left is trying to show you. As a function of different injected parameters equivalent with lambda sigma, stellar SNR, DIB SNR, I'm showing you the z-score in the recovered moments of the Gaussian. So the zeroth order moment, the equivalent with, the first is lambda, and the second is sigma. And so this is a validation of not only the bias, but also the uncertainties that we're reporting along with the parameters in our catalog. And what you can see here, hopefully, is that this is exactly a normal distribution. Okay, so this is exactly 0 in the center, and plus or minus, these are falling exactly on the one signal lines for the calculated width of this distribution for the recovery. That's true for most of the panels. The top left panel has a notable departure at the faint end, so this is the low EW end. That's just a detection threshold effect. right? So if you have a detection threshold, something that's just below the threshold that fluctuates high will get detected, and something that's just above the threshold that fluctuates low will not be detected. And that leads to this very characteristic positive bias that's very well known and well characterized. And that's even more clear in terms of div SNR, where you see the divergence. But other than that, I would argue this looks like a pretty good validation of the catalog. And we spent a little bit of time thinking about this low SNR bias, because not only is there a positive bias in the mean equivalent width, which is what I'm showing in the top panel here. So you see as a function of div SNR, you begin to diverge. It's pretty independent of the sigma of the div. But there's actually a bias also in the width of the Gaussian that you fit at low signal to noise ratio, which is a little bit less well studied. So we just wanted to show that. And so you overestimate how wide the div is if the true div width is small, and you underestimate it if it's larger. And that's just a grid effect because we're searching over a grid of sigma. So as you approach the boundaries, your posterior leaks out beyond the boundary of your grid, or vice versa on the other side. You could solve that by making a bigger grid. But we basically scanned all reasonable divs here, and the biases are quite small, and they're only at very low SNR. So we view this as a fine approximation. Okay, you can use these injection tests to estimate completeness. Using some arbitrary metric of whether or not a div was well recovered, you can compute a percentage of divs that were recovered as a function of points in parameter space, the true equivalent width and true sigma. And this is showing you that we're basically 90-100% complete for things that are 0.3, 0.4 angstrom equivalent with divs, if that number means anything to you. And the small trend that you see here is just saying that wider divs are slightly harder to recover at the same equivalent width. Right, so wider, lower amplitude things are harder to recover on top of a noisy background. That shouldn't shock you. And then to get to Gordian's question about how we chose 3.8 sigma, which might seem semi-arbitrary, is that you can use some notion, again, of completeness and correct recovery to make a true positive and a false positive rate as a function of the div SNR cut that you might try to impose. And this gray dashed line is 3.8 sigma. So we just chose it here to maximize true positive while keeping false positive as low as possible. And I would argue that this is exactly the regime you want to be in. And I'm happy to admit that one could move it left or right by epsilon, and I would be absolutely fine with that. So it's as arbitrary as you want there. I'll comment though that when people do these sorts of plots, they often restrict to high quality data that they understand very well. And I find that sort of offensive. And so the continuum normalization issues and heterogeneity that I mentioned is a real problem. And if you include that sort of heterogeneity in the data, you'll see that the gap here between the true positive and false positive rate is much smaller in reality. And so you're sort of sitting at 55 or 60% true positive rate and about a 10% false negative. 6% true positive rate and about a 10% false positive rate, which actually matches what I think is happening in our catalog. So I think that's a fair representation of the catalog. And that's really a problem of the upstream data that we can't get around. So this is sort of the best that you can do with the data that we have with our method. But I think it's still a clear improvement on what was being done before. Okay. Right. There are two more really, okay, the next two validations are most important, and then I'm happy to skip a few things depending on time. So one question that came up in the context of the study in terms of the validation of the methodology is that because we're doing a data-driven stellar model, what if some div absorption is in our training data, in our training set, and leaks into the stellar covariance matrix? So we make cuts on SFD and Planck to say that there's no dust along the lines of sight that we take the stellar spectra to, but what if there's still a little bit and we didn't know? Would that hurt our detectability of our diffuse interstellar band? I think it's a really important question and a very hard one to answer. So I will invert it and answer a different question, which is to say, if I intentionally put more dust in my training data, how much harder is it for me to detect synthetic sources that I've injected in? I can answer that question. So if I intentionally make the stellar prior a bit dustier, this is true equivalent width versus true div SNR. I'm showing you the change in the recovered equivalent width by making the prior dustier, by accidentally including what could be some div features into the stellar model. And what I want to show you first is that for a large portion of parameter space where most of our detections are happening, the change is tiny. It's 0.1% of the equivalent width of the div. And I argue that when you have a 0.3 angstrom div, that's totally negligible. Like we just don't care. This 3.8 sigma detection threshold is shown in magenta here. And what's shown in green in the bottom left are detections that are basically lost because we're using the dustier stellar prior. But I'll comment that all of those are below our formal detection threshold. Those were all sources that fluctuated high and happened to be caught by the catalog. So those are really not sources that you should care about because they shouldn't be making it into the catalog anyway. But I think this is a real nice validation that even with a little bit of dust is leaking into our stellar covariance matrix, it's not hurting our detectability. We're not missing thousands of div detections because we happen to be including some dust in our stellar model. Okay. Now to Vinay's question from a long time ago, which is, with a linear method and a single covariance matrix, can you actually marginalize over a large range of stellar types? This is a question that you should ask very early on in the talk, so I'm glad that you asked it. This is a stellar parameter space as described by GSP spec, the Gaia pipeline. This is effective temperature, metallicity, and log G. And these are all the public Gaia RBS vector released in that space. This isn't necessarily the true value for the star. This is just what Gaia thinks it is. And that's actually helpful to see what the pipeline is doing in its failure modes. This is a set of training data that we restricted to build our stellar covariance matrix. That's the subset of the area here. And what I want to show you is the average chi-squared per degree, total chi-squared per degree of freedom in this space. So what you should notice is that this value is extraordinarily close to 1 over a large range of space, what is clearly a large range of stellar types, and over a range of parameters that's much larger than the training data. So I think this shows that the model is generalizing.
The use chi-square is your calculation?
Yes, my calculation. I think this is showing that we're able to generalize and capture a large range of stellar types. And I'll say that I've thresholded the color bar here at the value of our total chi-square per degree of freedom cut. So stars that are extraordinarily hot and extraordinarily cold, and whether or not they're really hot or cold, or they're just hitting the end of the GSP spec grid because there's some bad spurious spectra that isn't being categorized very well and isn't even a stellar spectra possibly. I don't know, right? So we don't know what's going on with these stars, but I'll argue that it's a very tiny fraction. This is a log histogram, right, in total counts. It's a very tiny fraction of our data set. And so if more of our data were, M dwarfs, one might want to create separate models and try to handle it better, but it's clearly not affecting the vast majority of our data set here. And I was actually really impressed by what a large range of stellar types we are capturing by a single covariance matrix. Okay, I just want to say that the stellar model itself is doing decently well, and the stellar residuals are comparable or better to the best current synthetic model fits, which generally get the calcium triplet line to only plus or minus 5% if they're doing a good job. And here's just the stellar residuals stacked, and you can see that it's plus or minus 2% on the calcium triplet lines here. So there are some residuals, but they're as good as anything else. And we're marginalizing over them, and we're not falsely detecting stellar lines. So I think that's totally fine. Okay. Should I go all the way to 12:30, or do you want me to wrap up?
We did drop a few people, so it might be good to wrap up as
Quickly as possible.
Yes.
Okay, let me show 3 slides for the astrophysics, and if people have questions, I can answer some more. Oh, okay, it'll be 4 slides, but it'll be fast. So this is a these diffuse interstellar band catalogs are actually, in some sense, 4D dust maps, because you have detections of dusty lines of sight in the L and B, and you have the distance to the star at least. You might not know exactly the distance to the dust, but you know the distance to the background star. And then you have the velocity of the dust is moving at because of the redshift of the temperature. And so I'm just showing you here that most of the detections are happening in the galactic plane and they're associated with known dust clouds. And this just resembles a noisy version of a 3D dust map, right? And this is a top-down view, which also happens to look like a noisy version of 3D dust maps that you might have seen before. So we're really excited for DR4 because it'll give us a lot more data and a lot more coverage, all 5.5 million RBS vector that have been released. So it'll more than double the data that we have to work with. It's a factor of 5. Let me skip that and go to this one. This is the 4th dimension of our map, which is the velocity distribution on the sky in terms of the galactic latitude and longitude, and then a top-down view. And all you're seeing here is that the div is co-moving with galactic rotation. So you see this very characteristic positive, negative in the different quadrants.
How do you find the velocity of the div?
Because you know the rest, well, we learned the rest frame wavelength, and then you know what velocity you detected it at relative to the stellar.
But that means you know what's causing the dip, what line is causing it.
No, we don't know what's causing the dip. This is a slide that I'm skipping. But if you look towards the galactic anticenter, where if you assume the divs are somewhat, at least on average, co-moving with galactic rotation, you should see 0 shift in the wavelength. You can fit the wavelength of the unknown carrier, and then you can from that infer what you think the velocity distribution is. And so it's subject to the uncertainty.
So you're finding the divs to be clustered around the similar wavelength in all cases.
Yes, that was the Gaussian that I showed you before, right? And it was nice in that space rather than piled up on star lines.
Okay.
Right. Okay, so I'm skipping showing you the fitting of that, although the uncertainty, the error bars are quite small, and they're impressively small. And let me just end on a last point. So a lot of times, and maybe this isn't the most appropriate for this seminar, since a lot of us are statistically minded, but a lot of times I get asked, like, are these really high-falutin, full posterior Bayesian methods really necessary to get any astrophysics? I think the answer is, of course, always yes. This is a much better catalog. But let me try to convince you that that's true in a specific case. There's recently been a debate in the literature about whether or not DIBs, these diffuse interstellar bands, have been detected in the local bubble, which is a cavity blown out around our solar system. And the Gaia high quality DIB catalog came out in part support of this and said that they had some evidence that supported this theory by detecting this 8621 angstrom DIB in the local bubble. And I'll just say that by comparing all the spectra that they were making those claims on, we find no statistically significant detections in the local bubble. As parameterized here by our DIB SNR, I've color coded it, so anything 5 sigma or above is red. This is a 3D model of the local bubble. And all of these points, you can see that are red are falling just outside of the local bubble. And the only points that you see that are inside are blue, they're less than 5 sigma detections. And the exact number that you find inside this local bubble is exactly what you'd expect for a 3.8 sigma cut, given the number density of sources that are inside the local bubble. So I think that's a really nice validation of our DIB SNR.
So who was saying that there might be DIBs in the local bubble?
There have been a couple of groups, but in part the Gaia DIB paper said this.
Oh, really?
Yes.
Okay.
It's actually it was in the abstract and conclusion. It was one of the main claims of the paper.
Oh, okay. I missed this.
I argue that it's not true, or at least
I mean,
we don't.
I would be very surprised.
I would argue that we don't have the evidence to say it's true yet. So, and let me be cautious because there's another 4.5 million spectra that are private that were involved in their catalog. But if I do an apples to apples comparison on only the public spectra, which is what I've been showing you, they have false detections where we do not. So this is a 2D version of the plot on the left. This red point is actually outside the curve in a 3-dimensional model, but okay, it's 2D projection. And this is the plot that they have on the right. So this is what I was asked about earlier, is do we have any agreement on the metric of goodness? Well, essentially their notion of DIB SNR shows many 10 sigma detections in the local bubble, which is totally against any physical intuition that we have, and is not what we have using our very, was in my opinion, a much more statistically rigorous approach. So I think this should convince you that our catalog is better, and that yes, doing stats is important for astrophysics. But you're convinced? Okay, well, I've convinced one person in the room. Okay, so let me end here. Sorry for going 7 minutes over, and I have more astrophysical slides if people are interested. But let me just conclude by saying that I've shown you a new DIB detection method that I then applied to the Gaia RBS spectra to create a new 8621 angstrom DIB catalog that is free from detectable stellar contamination. So back to this plot that I showed at the beginning to motivate. I'm really excited about applying these methods to look at the multiple near infrared DIBs that are in apogee and look at how they covariate with each other, for example, and how they vary across this really beautiful and big data set. If you are interested in looking at our catalog, any of the components for either model, for all 1 million public RBS spectra or the code, all of that is always available on our website at this QR code that you can look at and download. I think you also linked it in the abstract in the email. And I'll just conclude by saying that, of course, I have really great collaborators that made this project possible. Catherine, Josh, and Doug Finkbeiner, my advisor, who, as I promised, appears on the slide. So with that, I'd be more than happy to take any other questions. I know we had a lot of them during the talk.
Any questions from the peanut gallery?
Maybe all the question askers left.
Yeah, I mean, the point was that, we've asked all the questions along the way. So. I did have that one question about, how you find the velocity of the thing, but then you answered that too. So. It looks like there are no questions.
Okay.
So, yeah, that's
A
good.
very trivial question. You published about 10,000 stars. How can this data be 500 gigabytes in size?
Because it's all models for all 1 million spectra with and without the DIB. It does not include, like there are only 10,000 stars that have DIB detection, so we show the decomposition for all spectra, which I think is the right thing to do.
Yes.
That blows up. And because you have 3 components, right? Because you have DIB plus star plus noise for everything. So everything gets multiplied by a factor of 3.
Yeah.
Actually 5 because you have the star plus residual for the other model. So it's a lot.
Yeah, so I have a question. I don't know if it's good or bad question, but I was just thinking if you could apply your approach or your model to quasar spectra to look for, the differences between different types of quasars in optical.
That is a good question. We're always looking for other applications. Let me not answer your question first and say something entirely different, and then I'll come back to your question. One of the ways that we've been applying this method is to ask whether or not, and have a nice detectability of spectroscopic binaries. So you can put down one component of one star, then you can ask, is the total chi-square degree of freedom still high? Is it possible that there's another star at a slightly different velocity that has all of the correlation of all of its lines? And you can get a much better, much lower SNR detection of spectroscopic separation of binaries that way, to much lower separations in velocity space. So that's yet another application that we're looking at. Asking about whether or not you can tell different quasars apart, I mean, I would probably build a covariance matrix model for one type and another type, and then just ask which one is more consistent with in terms of the way that all the lines could vary. I can imagine doing something like that, or if you're interested in a specific line, trying to measure its line on top of some crazy continuum, and then and ask for a statistically rigorous measurement of the equivalent width of that line. Both of those things I think would be possible, and all you have to do is build a data-driven, pixel-pixel covariance matrix to do it, which I think is part of what makes this method so extensible. So in short, I think the answer is yes. You just have to think about the actual framework for how to apply it.
Yeah, and actual application, which I'm thinking about. So maybe we'll chat at some point.
Sure. Yeah, I'd be happy to.
Okay, because it's kind of an interesting, I mean, maybe interesting approach.
Yeah, I just want to comment though that this is optical and near infrared, where we have lots of counts and uncertainties are Gaussian. No promises are being made about the Poissonian limit. So that's the one caveat that I'll say.
Yeah.
But I mean, everything in here should generalize to the other noise statistics.
I agree.
You can't derive your analytic noise posteriors.
Yeah, you don't have
I mean,
analytic-
in theory, those. Oh, well,
I'm not sure it's closed form,
Yeah.
but what
I mean,
Gordon's
there's
saying
another
is that
approximations too, right?
they
Because
do, yeah.
Anyway.
So you could impose the Poisson model. I just haven't developed the code to do it. That's all I wanted to say. It's possible for sure.
But another question: how many stars did you use for the marginalization? Is it dependent on whether you can, or is it strictly dependent on the true data-driven stellar models? I mean, I think that's a better approach. But can you also use synthetic stellar models and then marginalize over those?
So what we're doing in Apogee is using the synthetic stellar models.
Okay.
And so of course you can, but then you've committed to the line list of lines that they've included in models synthetically.
Yes.
And so you'll be sensitive to lines that aren't being modeled. But in fact, because I'm part of SDSS and Apogee collaboration, I am interested in telling them which lines they need to go back and tune. So I don't mind doing that. I'm not part of Gaia, so I can't force them to tune their line list. But yeah, but that's the only problem with synthetic models, is that you then become restricted to what's in the model. But yeah, of course you can.
Yeah, I'm asking specifically regarding the quasars. Do we have enough? I don't know how many quasar observations there are. Do we have enough to marginalize over for your method?
I don't know. That's a question for Netta. I mean, I guess, but Boss has quite a few.
Yeah, I mean, SDSS has thousands or millions, well, hundreds of thousands of spectra. I think we have
That sounds sufficient to constrain a low rank covariance matrix.
Yeah, I think it would be fine.
Okay.
Well, it's definitely a smaller parameter space than million stars, but yeah, there is more and more quasar spectra being.
Yeah. Okay. Right. That's also true. Yeah.
Yeah.
There's no other questions. So.
All right, if there are no other questions, I'm going to stop recording.
Great.
Going once, going twice, and there is a button here.